a document that is all details about.
Okay, my apologies there. Let me check to see the audio is working. Yep, we're good. Okay, so I have informed you that this class is hard. So in that spirit, this is today's lecture. We're going to do a hard problem. Except the problem is, this is not a hard problem. But it's really difficult for novice engineers to really wrap your mind around this, because it's a lot going on all at once. I threw this problem at my brother, who he's old, and he's an engineer. He smells funny, but oh dang, I'm live streaming this. He's gonna find out. But I threw this problem at my brother, and my brother's like, oh yeah, here's how you do it. He knows exactly how to do it. He knows how to calculate moments and torsions and all of that, and it's second nature to him. I want to get you to that place, but I gotta scare you with a problem first. And that's what we're doing today. So it's not really scaring you, it's talking through a very challenging problem, how to go through the process. To summarize everything that we've done so far this week, you have the 4 different types of stresses. Okay? So we've got normal stresses, and we've got shear stresses. Okay? We have 4 different kinds. Normal stresses can be caused by bending moments or by normal forces or axial forces. Okay? In normal forces, sigma x is equal to fx over ax, where the stress is in the same direction as the force. So you could replace all these x's with y's. Please also keep in mind that ax is sometimes also referred to as ayz, because it is the area in the yz plane. But it's also called the x-plane because the x vector is perpendicular to that plane. I think I said that like 3 or 4 times in my lecture on Monday. Okay? The other normal stress causes tension and compression loading, but it's caused by bending moments. Okay? As we talked about, when you have a beam that bends, the top will be in compression and the bottom will be in tension. Or you flip it around and the bottom will be compression and the top will be in tension. Those are normal force stresses, but they're just on a smaller scale. And sigma here, sigma x, is equal to m, the moment that occurs in either the zz direction or the yy direction. Could be either one of them. Divided by ixx, which is the moment of inertia in the x direction as seen from the x side. Okay, and again, you can switch all these variables out. So if this could be sigma yy, and then it could be either an mx, mxx, or an mzz with an iyy. As long as this and this are the same, and this are not the same, that's how that formula correlates. So on the other side, we have shear stresses. Shear stresses cause warping of the material. These two cause elongation or compression. These two cause warping. The 2 sources of shear stresses are shear forces. And here, the equation for that is tau yx is equal to v in the y direction divided by a in the x direction, or could similarly be v in the x direction divided by a in the y direction. Okay, you see the yx here, you have a y and an x. That's where it shows up. But this is then multiplied by a scalar factor c, which I believe is in table 3.2 in your book. It just gives you the maximum shear stress value. Can you see that, Sky?
Yeah.
Okay. It just gives you the maximum shear stress value, so that you multiply this by 3/2 if it's a rectangular beam. You multiply it by like 1/3 or 4/3 if it's a circular beam. It just gives you a value to tell you, okay, here's how you calculate the maximum. And then the last shear stress can be a result of torsion. Okay, and here, torsion, the problem with torsion is that torsion occurs in multiple directions based on where you're looking at it. So let's say I've got a circular beam like this, and I take this circular beam and I apply it in torsion, which means it's being torqued around the center line here. And if this is my, let's say, this will be the y direction, this will be the z direction, and then my x direction comes out like that. If I do this, then here this is along the x-axis. At this place right here, there is a shear stress on the x-plane that goes in the y direction. This right here is tau xy. At this location here, there is a shear stress that is pointed in the z direction. Up here, this is a tau xz, or a tau zx. Okay, so depending on where you're looking, right here, this has components in both tau yx, tau xy, and tau xz. So it basically forms a sinusoidal function where as you travel around the circle like this, tau xy and tau xz, the vectors all sum to the same vector. They have the same magnitude, total magnitude, but sometimes that magnitude is more in tau xz, such as when it's straight up and down, or more in tau xy. So it is a little bit different to visualize torque, but you have the same constant torsional stress all the way around, but that changes direction based on where you're looking at it. Is that going to be problematic for you in this class? Yes. Okay. Is there a way to nicely compensate for that? Well, unfortunately, no. You just gotta memorize these things. The stuff that pops out, you have to be able to pull it out of your brain box. So this could be either tau xy or tau xz. Again, depending on where at this beam you're looking. And this is equal to T, which is in the xx direction. It's a torque that is axial in the x direction along the x-axis, times the radius r, which is the distance from the center axis to wherever you're calculating the stress, divided by j in the xx direction. So these are the formulas that we use to calculate what individual components create stresses in a system. Okay? What we got to do now is we're going to take these equations, which I'm not sure the live stream, I'm not even sure that shows up on the live stream.
Yeah, what's J?
J is the polar moment of inertia. I'm going to move the camera closer because I'm not even sure you can see that. Okay. Well, thank you, Jackson.
You just might want to rewrite the 3 in table 3.
Yeah. I knew that was poorly written the moment I did it. Okay. I guess this would be harder to watch on your phone, but. All right, what we're going to do is we're going to do an example, okay? Because I love you, and because tonight I want this to show up in your nightmares. So once upon a time, there was a gear exchange. It's just a gear shaft. It had 2 gears on it. Like this. Okay? And these 2 gears were held in place with a bearing on both sides. But there's a little bit of a gap between the gears. Maybe it's because for some reason it needs to have some kind of a separation or something. Okay? So what we're going to do is we're going to take these 2 gears, and at the top of this gear, I'm going to apply a force in this direction that is equal to FG1, because this right here is going to be G1, it's going to be G2, this is going to be B1, this is going to be B2, because we got 2 gears, 2 bearings, and I am horribly unique when it comes to naming things. I love consistency. Ugh. So we're going to take a force, we're going to apply it here. And we're going to take a force on this gear, and it's going to be applied in this direction. And this is going to be FG2. Okay? Now I'm going to go ahead and I'm going to write the components here. I've got, well, my coordinates. Okay, this is going to be the y direction, this is going to be the x direction, this is going to be the z direction. Okay? So if I were to write out the vector components for FG1 and FG2, it looks like this. FG1 vector is equal to, we're going to say it's equal to 860 pounds, and it is entirely in the z direction. So that is K, not J, that I just wrote. So that vector is 860 pounds in the K direction. FG2 is equal to 1720 pounds in the J direction. Everybody following so far? Okay, things are about to get nuts. First, I'm going to give you some sizes. So I'm going to draw the XY plane of this component just so that I can give you sizes and dimensions. Okay? So we have this here, we got this thing here, we got this here, we got this thing here, and then we got this thing here. Okay? Any questions? No? All right, I'll see you guys next week. So what we'll say is we're going to have the bearing located here. We're going to say that the bearing is located 1 inch in from the end. We will say that this bearing is located 1/2 inch. The center of that bearing is located 1/2 inch from the edge of this gear. This gear is going to be 1 inch wide. These gears are going to be 4 inches apart. This gear is also going to be 1 inch wide. There's a bearing here. The center line of this bearing is going to be 1/2 inch away from the gear. And then the center line of that bearing is going to be 1 inch from the edge. Okay? So 1, 1/2, 1, 4, 1, 1/2, 1. There, it's symmetrical on both sides. Now as for diameters, the shaft diameter here is 3/4 of an inch. The gear diameter here is 4 inches. So this will be DS1 for the diameter of the shaft. This will be DG1 for the diameter of gear 1. This will be DS2, and that's going to be equal to 1 inch. And then we have DG2, which is the diameter of gear 2, and that's going to be 2 inches. And then DS3 is equal to 3/4 inch again. Okay, so it's 3/4 inch, 4 inches, 1 inch, 2 inches, 3/4 inch. And we're going to assume that this is solid circle material. We could have made this a tube. In a real application, there's no reason why you wouldn't make this a tube, but I made it a solid circle because it does make the math a little nicer on our end. And we're, boy howdy, we're going to be doing a lot of math. So, class is fun today. All right, any questions so far? How do we solve this? What's a gear? What is a circle? Exactly. Well, we know that we're going to treat this as if it is one component. Okay? This isn't multiple components. This is one component. We have broken this free body diagram down into its most fundamental state. We're not dealing with a system now. We're dealing with a single component and how it transmits those forces along that component. Okay? So that is the first step would be, if this wasn't a single component, you take the system, you break it down, you do the free body diagrams of the systems, you find out what the forces are exerted between components, and then you do free body diagrams of components. Okay? Here, we are at the component level now. This is no longer a system. Once you're at the component level, then you can start looking at stresses. At the system level, you can't look at stresses. At the component level, you can. Okay? Well, we have 6 total equations that we can generate from this system. We have, does anybody know what those 6 total equations are?
Some of the forces in the X, Y, Z, and then
Some of the forces in the X, some of the forces in the Y, some of the forces in the Z direction, some of the moments in the XX direction, some of the moments in the YY direction, some of the moments in the ZZ direction. 6 equations. In order to generate these equations, you will not be able to use one single view from a free body diagram. You can't. It's too much. If you can visualize this component in your head, you can rotate it, you can try doing it that way, but you're still looking at a free body diagram in 3 different directions. You have to do all 3. So, we're going to start I am way too easily amused. Yeah, in the freshman class last week, I was doing the live stream and I started playing the link to the YouTube video of my live stream. So I was live streaming myself watching the live stream, and then the video was catching up. So then I was live streaming myself watching myself doing the live stream. And it ended up, I did that for like 5 minutes before I broke myself. It's fantastic. We're going to start by doing free body diagrams, okay? Because that is where you should start. You have 3 free body diagrams that you can come up with. What is the first one that we should do? Or does anybody know what are the 3 free body diagrams you come up with?
X, Y, Z.
The x-plane, y-plane, z-plane. Okay? What do you say we start with the x-plane? Okay? So for the x-plane, by the way, that's what the X-Men all write in. The x-plane, the coordinates that you see are in the y and z direction. So what I'm actually going to do, make this a little easier, I want to look this direction down the shaft, just because I can. So if I'm looking that direction, z is going to be pointing this way. So when I draw my coordinate system, there's y, z. Now you can, if you look at it from this end of the shaft, your coordinate system will look normal. It'll look like this. I didn't want to. So I'm making things challenging. But if you wanted to do this, and you wanted to look from this end of the shaft, be my guest. It's not going to hurt me at all. Okay? You have the ability to switch your coordinate systems as you wish, as long as you stay consistent between all of your free body diagrams. Okay? That is the key. If your free body diagrams all have the same coordinate system, you're golden. All right. So now taking this from the x-axis, we see the shaft, which is right here. Behind the shaft is this gear, which has a diameter of 2 inches. So I'm way overdrawing that. We can't really see this shaft because it's kind of behind everything. But then we see this gear, which has a diameter of 4 inches. And then there's this shaft, which again we can't see because it's kind of behind everything. So this is the component free body diagram. Now we're going to go ahead and add in the forces. Okay? Now I'm going to assume that I'm going to write down an assumption here before we get going any further. Okay, bearings. The purpose of a bearing is not to exert a moment on the system. Yes, bearings do have friction. Yes, that does create a moment. We're going to assume that that is negligible for this system. Okay? Because it kind of makes the math a little bit uglier. And you have to know what that frictional value is and associate it in to figure out it. You know what? I don't want to do that. Let's just focus on the power transfer here. Okay? So we're going to assume the bearing does not provide any moment at all. We're also going to assume that the bearing does not provide any x-directional forces. Okay, we don't have any x-directional forces acting on this system. So if we put an x-directional force on these bearings, let's say we locked them down. If this shaft expands even slightly, those bearings are now exerting a force against each other and putting the entire shaft in compression. That's not good. So does that happen? There is somewhat of an x-directional component to these bearings, especially if they're press fit. But we're going to assume that the shaft has the ability to slide as needed. It just doesn't because the bearings are butt up against gears. So, with that said, there's only 2 forces, 2 directions that the bearings can provide forces in. No moments. It's not doing any of these 3, and it's not doing this one because the system can slide out that way. Assume bearings only provide force in F, Y, and FC directions. Nothing else. Okay? But now what that means is we have to draw in the forces that are created by the bearings, the F, Y, and FZ direction. So first, when you start with your free body diagram, you always start with applied forces. Step 1, applied forces. What are our applied forces in this system?
FG1.
FG1. FG1 is in the Z direction at the top of that gear. So we're going to go ahead and say it's in the positive Z direction. That is FG1. What other applied forces do we have? We got FG2. FG2 is located on this face of the gear and it is facing upward. So I will draw it here. I'm going to extend it up. FG2. Do we have any other applied forces? But our system is not in equilibrium.
From the bearings.
Bearings are boundary conditions. Does anybody remember what the difference is between an applied force and boundary force?
Boundary force only exists in opposition to applied force.
Boundary force only exists in opposition to a movement. So here, your shaft is not just suddenly going to start lifting up in the air. And the force that's preventing it from doing that is a displacement boundary located at the bearing. And that bearing will provide sufficient force to prevent that shaft from traveling upward. Okay? It's a contact force that has to be present that pushes in whatever direction. Now usually these bearings are press fit, which means it has the ability to provide a force from any direction as needed. It'll contact the bearing, it'll push that way. Somebody from the last class pointed out that is there, if we're looking at this, more than likely our bearings are going to be pulling down and opposition is pulling up force. Is there an upward facing component to this bearing force? And the answer is probably yes. The bearing is press fit on the shaft. It's going to be squeezing on the shaft at that location. And that is going to put an upward force. Now the net force exerted by the bearing on the shaft is going to be overall downward because it's opposing this force. But there is some component, vertical component, upwards from the bearing just because it's a press fit on the shaft. But mathematically we can just ignore that. So we'll draw this down. And I'm going to draw two vectors because one of them is FB1y and the other one is FB2y. We've got bearing forces in the y direction. And then we've also got z directional forces. I'm going to draw them opposite of FG1. You can draw them in the same direction. You'll just get a minus sign in the math later. And this is FB1z and FB2z. My 2's look like z's, but that they're distinctly different. Do we have any other forces acting on this system? We have two applied forces. We have boundary forces that we are assuming for both bearings. We may find them to be 0. Who knows? We're still going to have them show up in our equations. Okay? We're done with this one. Now you said the next one is, we did x plane, we'll do y plane. What two coordinates show up in the y plane? X and z. Okay, so let's see. Looking at this, I would like to look at it from the top. So I'm going to go ahead and put x, z like this. Okay, you can switch it around however you want. I just would like to look at it from the top. If you look at it from the bottom, your x and z, it looks, the z is flipped if you look at it from the bottom. Or you can turn it around and you can switch the x around if you really want. You can make the coordinates do whatever you want. You just have to stay consistent. This, looking at it from the top, makes the most sense for me. Okay, so I'm going to go ahead and I'm going to draw this picture again, because it happens to be circular. It isn't terribly interesting here. Okay, I got my bearings there. I got my gears. Now, y directional forces will not show up in the y plane. Okay, if I were to make that show up in the y plane, let's see, which one's the y directional force? This one. It would show up like this, which we don't need to draw because that does show up in both of the other planes that we're drawing. So we don't need to focus on any y directional forces in this plane. We're not going to be able to figure out the moments caused by any of them. They don't matter in this plane. Okay, so we are going to ignore the y. So here, we do have to put the z directional force. Now I'm looking at it from the top. This force is being exerted in the positive z direction, and it occurs at the center line of the gear, FG1. Now, based on here, we drew these two forces in the negative z direction, which oppose this. So we're going to see FB1z and FB2z. Any questions so far? Does this make sense? I'm trying to do this step by step as step by step as possible. Okay? If you start getting a glazed over look, it's okay. I'm live streaming this. You can go back and watch it later. You can watch me pace in front of the camera a few times. Fantastic. I probably will go back and watch that part specifically. I really need better hobbies. Okay. Oh, hold on. So, this is the applied force that shows up in this plane. These are the boundary forces that show up in this plane. Right? Because we only have boundary forces because these are our two boundary conditions. So the question is, are there any other boundary forces? Are there any other applied forces that show up in this plane? In order for there to be a boundary force, it has to be contacting something else. This component is only contacting the bearings. So we're going to assume, well, and the gear connections, but we put those as applied forces. We're going to assume that this is floating in space, only held up by the bearings. So no other contacts, no other boundary forces. That's all we have. So let's do the z-plane. Okay, and for here, I want to be looking this direction at the component. So what direction is my y going to be facing? Up or down? Okay, we got y up. What direction my x going to face? It's going to face to the right. Okay, so finally, a normal coordinate system. Finally. Okay, I will redraw this. All right, what applied forces show up in this view? FG2. FG2 is located at the center of G2. It's in the positive y direction. FG2. What other forces show up in the z-plane?
P1y or Q1y.
Okay, we're gonna, here we drew them in the negative y direction to oppose this vector. So we'll draw FB1y and FB2y. It is important to make sure that your direction on this free body diagram matches the direction here. They're both in the negative y direction. They should be in the negative y direction in both drawings. If they're not, you did something wrong. Similarly, FB1z, FB2z are both in the negative z direction in both of these drawings. That is also very important. We have to maintain consistency. Consistency is the key to success. Okay? So now that we got all of our vectors drawn correctly, we have everything labeled, all of our components in, we have 6 equations that now we have to fill out. The nice thing is, these 3 equations, for each one of them, we can get them off of 2 different drawings. Okay, I can sum the forces in the x direction in any place where the x direction shows up, which is these 2. Let's start with that one because that one's the easiest. Sum of the forces in the x direction is going to be equal to
0.
Yeah, but what are the forces in that direction? There are none. Which is what makes it easier. I like picking on you, Walker. You're always such a good student. All right, now we have the forces, the sum of the forces in the y direction. Okay, now once again, we can do our sum of the forces in the y direction from either of these drawings where the y forces show up. I can promise you this one's going to be easier because there's only 3, whereas this one has, what, 6? So it's probably going to be easier to do this, but you can still get them off of this drawing, even though this drawing is a mess. So what are the forces in the y direction? What is the sum of the forces in the y direction equal to?
G2 minus FB1Y minus FB2Y. Won't FB1Y and FB2Y be the same?
No.
Why is that?
Oh, you're getting ahead of me, man.
G2 is closer to FB2Y.
It all depends on the moment. What this is because it's a shear load, there's going to be a moment associated with it. The whole axle is going to be in bending. Now, because these 2 are closer together, this is going to carry more of that load than this one is. Yeah, I was actually driving home from work yesterday thinking about what would happen if you could make a gear that was also a bearing so that the force was just like right there. And then I was like, wait a minute, that sounds really dumb. So I stopped thinking that. Because in reality, that increases the amount of force that's carried on this bearing. It means no force is carried on this bearing from this load. Well, that's kind of dumb. It's unnecessary. You increase the force here? Why? Why would you want that? You don't have bending moment load. I guess if you had a really long shaft that you had to carry a torsional load over, then that would be valuable. But otherwise, not really. And even then, you just, like this, you put the gear right next to the bearing, it minimizes that vertical load. Now, if you put these 2 gears right next to each other, it even further minimizes that bending load. The closer all the components are together, the better off everything is. Especially when it comes to shafts like this. Okay? Sorry I got off on a tangent there. So here's the equations for the y direction. Sum of the forces in the z direction. What does that equal to?
FB1 minus FB1C minus FB2.
And that equals to 0. Why? Because we are not seeing any acceleration on this system in the y, z, or x directions. Okay? Awesome. That's 3 of our equations down. Now it gets to the a little bit uglier part. The sum of the moments in the x direction. Which of these views do we have to look at? Yes, the x-plane. Did you guess that or did you know?
I did.
Nice work. This is where all of our x-directional moments are going to be. Okay, it's in the x-plane. We see it in the y-z direction. all of our moments are going to be about the central axis because this is a rotational system. That is a boundary constraint, can't rotate about any other component. So what we have is all of our forces also happen to be perpendicular or pointing directly into that axle. The nice thing about that is these do not create a moment because they are radially directed towards the center of the axle. That's going to happen here no matter what. Because if we look at that bearing, okay, let's say here's the bearing housing. Okay, and you got a shaft in here like that. I'm drawing it intentionally really small. Normally they're about the same size. This is going to contact right here, and the contact force has to be normal. A normal force exerted on the outside of a circle always points to the center. So these bearing forces are always directed radially inward or outward. Always. Which means they do not create a moment. Bearing forces do not create a moment. Unless it is a motor bearing whereby there's a torque applied at that location, but you will be given the torque if that's the case. And also bearings do have some friction, but it shows up as a torque. It doesn't occur because these are offset forces. These are radially inward, which means these forces point towards the center. They do not create a torque in this system. Okay? So we have 4 forces that do not create a torque on this view. We have 2 forces that do create a torque. What are the formulas for those? Force times the distance is equal to torque. Yes. So which one of these is going to be producing a positive torque? Okay, I'm hearing both. Let's use our right hand rule. Right hand rule, you slap your palm on the radius from the location to the vector. You curl your fingers in the direction of the force vector, and your thumb points out to where it is. Here, this is positive. FG2 is negative. What is the distance from the center of the axis to FG2? What? It's 1 inch. Because this is a diameter. It's one of those gotcha things that comes to circles. Dang you, circles. I'm just going to go ahead and say it's 1/2. This is 2 inches. Because that's DG1. 1/2 DG1 times FG1 minus 1/2 DG2 FG2. It's equal to 0 because we're assuming that this system is not accelerating. It can accelerate. If it does accelerate, then these two should not equal 0. And if it does accelerate, you'll be given both FG1 and FG2. I gave you both FG1 and FG2. And the way that I gave them to you, these cancel to 0. Surprise. This equation, unfortunately, doesn't tell you anything. If you didn't know what FG1 or FG2 was, and you were only given one or the other, you use this equation to figure that out. Because this one is the torque equation for the system. This directly correlates those two to each other. Now I'm going to write the other 2 equations quick because class is about over. MYY. The only place that shows up is in the y plane. You can take your moment about this point, or this point, or this point, or this point, or this point. You can take your moment about any location you want. Generally, it's a good idea to take it about one of your 2 bearing forces because you don't know what those are. So we're going to go ahead and take it about FB1Z. So we'll say our moment is on the center line of that axle at FB1Z. The moment about FB1Z is going to be, okay, FG1 is going to create a negative moment, and FB2Z is going to be a positive moment. So we'll say negative, let's say that's 1 inch times FG1Z Nope, just FG1 plus, okay, this is 1 inch, 1.5 inches, 5.5 inches, 6.5 inches, 7 inches. 7 inches times FB2Z, and that equals 0. Okay, we know what FG1 is. We can figure out what FB2Z is from this equation. Last equation, sum of the moments in the ZZ direction. Once again, you can only use the Z directional plane to do that. This guy picked up on that right away. This is true. You have to use the Z direction plane. We can take our moment about any one location. For poops and giggles, I'm going to go ahead and make it about here, so that now we're solving for FB1Y instead of FB2Y. Just for fun. Okay, so here, FB1Y creates a positive moment. FG2 creates a negative moment. So the distance from here to here is 1 inch. So that's negative 1 inch times FG2 plus, by the way, the difference between the bearings is 7 inches. So that's 7 inches times FB1Y equals 0. This is all the equations that we have. Using these 6 equations, we can solve definitively for what those last 4 forces are that we don't know. Any questions? I'm going to continue this example in the online lecture on Monday. So be looking for that. You have a homework assignment that has been posted for next week. I'm still working on posting the quiz for next week. That will be posted this weekend. Okay? This week's homework is hard, and it will take you a while. Do not put it off to the last night.
When is the last night, isn't it?
Well, for next week. The stuff from this week wasn't that bad. The stuff from next week is